Hello. Hi. Hello. Am I audible and is my video visible?
Yes.
Okay, yeah, thank you. So good evening, everybody. I'm sorry, I'm not keeping quite well today, so I might speak a bit soft. So if I'm not audible at any point, please let me know so I'll try repeating it. So I think we have a good number. So let's get started. I'll just share my screen. Right. Yes. So once again, good evening everybody and welcome to today's live tutorial on urban utilities planning, water supply, sanitation and drainage. So I guess I can see two new faces. So I am Jeslu. I'm a Prime Minister's Research Fellow at IIT Kharagpur and I've been working with Professor Pandit for the past 4 years. So I'll be handling all the live sessions for this tutorial. So today we will be discussing about week four's content, and we'll try to solve certain numericals and certain theory questions related to what we discussed in week four. So in week four, we mainly discussed about pumping stations. So we discussed on why do we need pumping stations. For some situations, we might need a pump to take water from the reserve from the water source, such as surface water source, and we'll need it there, so only over there. So then that becomes a single point pumping, or we'll need it while taking it from the source as well as while pumping it to the distribution system. So it becomes a two-level pump. So like that, we discussed about where all pumps are required. Then we learned about different types of pump, booster pumps or high lift pumps. We also discussed how do we size pumps, or what is the lift that is needed, so which comprises of the suction lift, the discharge lift, the lift to accommodate for friction. So all these we did certain numericals in order to calculate the lift of the pumps. Then in the last two lectures, that is lecture 19 and 20, we looked into service reservoirs. So why are service reservoirs used and what are the uh, factors or considerations that we need to look into while designing a service reservoir? How do the capacity or the topography of the region, and based on these variations, how do we plan our service reservoir? We also looked into strategies or methods by which we can calculate the capacity of the reservoir. One common method that we usually use is the mass curve method. So we discussed that in detail, and we also try to solve certain numericals using the mass curve method, where we find based on the supply and the demand that is there in a region, we try to find what should be the capacity of the reservoir. So these are the theory parts which we discussed in the lectures. So today we will try solving certain numericals based on this. So so since there are few new participants, so this is how we'll be going. We will go question by question, and after each question, you can ask doubts regarding that particular question. And towards the end of this today's session, we will have a 5 to 10 minute discussion on any other question that you want to discuss regarding week four or one, two, three, four, any of the weeks which we have passed. Week five, we will not be taking up today. So feel free to let me know if I'm not audible or if my video is stuck anytime. So let's try solving together. So let's get started. So the first question says a city has a population of 1,50,000. Water is to be supplied at the rate of 160 LPCD. If the lift of the pump is 40 meters, calculate the brake horsepower. The rising main is 300 meters long with a diameter of 50 centimeter. Assume that motor efficiency is 60% and F is given as 0.01 and the peak hour demand is 1.5 times the average demand. The efficiency of the pump is 85%. So we have a lot of information given over here. So firstly, we have been asked to find the brake horsepower. So that's the question. Uh, we have to find the brake horsepower. So let's just write down what all is given. So we've been given the population, which is around 1,50,000. So 1,50,000 is the population of that region. Then the water supply rate is also given. So the supply rate is 160 LPCD. LPCD stands for liters per capita per day. So for 1,50,000 people, like for one person, we have got 160. So for 1,50,000 per people for that region, we'll have to multiply it by 160 into 1,50,000. So that we will do later. So I'm just writing it over here. So our supply rate is given as 160 LPCD, and yeah, the lift of the pump is given as 40 meters. So that's already given, the lift of the pump. So by this lift, what is meant over here is this is the lift of the pump, what is there. So by learning about lift of the pump, we learned the head of the the lift of the pump will depend upon the lift due to suction, the lift due to discharge, and the lift due to friction. So in this particular case, it's the suction plus discharge. This is where the pump is being involved, where the pump. So why this is there, I'll just explain that. So imagine we have a water body somewhere over here, and then our pump is situated over here, and then we have our overall reservoir somewhere over here. So we need to lift the water from this level to the pump level, which accounts for our suction lift. And now we need to, like, since this is located at a certain distance, we need to take this water from here to this point. This accounts for our friction lift, which is this. And after reaching this point, we need to take it up again. This accounts for our discharge lift. So there are three components. So we have the suction lift, we have the discharge lift, and then we have the friction lift. So what we are talking about in case of the pump, where pump is pumping this higher, so that accounts for both suction and discharge. Friction is not considered over there. The distance it has to travel is not considered over there. So in this case, yeah, so we have the rising main is around 300 meters long with a diameter of, yeah, so rising main is 300 meters long with a diameter of 50 centimeters. So this information we will be using in order to find our friction lift. So we have, so I'm just writing the information. So our rising main is about 300 meters. So this can be the other way also. Like for instance, here I mentioned that the reservoir is somewhere there. Now, it can also be that you have a water body, you have the pump, the reservoir is there, so you're lifting it up. But to supply to the distribution system, later you need to again push it to a certain distance. So the idea is you have a suction and then you have a discharge, and after that's the main supply. For instance, if you're giving it to the distribution system, then the distribution system is at a distance, so you have a distance of about 300-meter long, and the pipe which is used in order to trap or to take this water to the distribution system has a diameter of about 50 meters. So this we will use in order to, yes, so this we will use in order to find the friction lift. So that's what, so the diameter also I will write. It's written 50 centimeters. So since we are using the standard units, let's convert it to meter and write. So now efficiency. We also, the next information which was given is the efficiency. We've been given that the motor efficiency is 60% and the efficiency of the pump is 85%. So the question asked to find brake horsepower. Now, brake horsepower is equal to our water horsepower divided by efficiency. This is the formula that we learned. Now, why we're doing this is because water horsepower is the actual power which is consumed, or actual power, yeah, the actual power or the actual work which is done, the actual power. But brake horsepower talks about the one which we are actually experiencing, because the pump or the motor which is used will consume, or there is some loss of work done, there's some loss in the work done due to the motor or the pump that we are using. So after accounting for this loss, so this loss comes in the efficiency. If the pump is more efficient, that means there will be less loss, or if the motor is more efficient, there will be less loss. So that is taken care of this efficiency term. And considering that, we will get the brake horsepower, which is what is actually experienced. So this is what is actually put into the system, and this is what is actually experienced, or the output, whatever is there in the system. So we need efficiency for that. In this case, we've got two efficiencies. The motor efficiency and the pump efficiency is given separately. So which one do we use? There would be a confusion in that. So we will have to use both, because uh, the pump itself, if the pump itself is taking some amount, if the pump itself is losing some amount of work which is done, that also needs to. So here about 15% is lost in the pump. Then another 40% is lost over here because of the motor which is using. So both needs to be considered. So let's write that down. So we have efficiency of the pump to be given as 60%, and then the efficiency of the motor to be given, or did I write it wrong? Sorry. Efficiency of the motor is given as 60% and efficiency of the pump is given as 85%. So let the information be there. Then we have F. F is our Manning's coefficient, which we use in order to find our friction. In order to find the head due to friction, we need the Manning's coefficient. We also learned about another coefficient. Can Does anybody remember which was the other coefficient which we learned? It's called by the name F dash. This was Okay, so this was Darcy's coefficient. So we can use both. So the equation mainly uh, writes it in terms of f dash. So we have the relationship which says that f dash is equal to 4 times f, 4 times f. So in this case, our f is given as 0.01. So our f dash, the Darcy's coefficient, is 4 times 0.01. So this information, we'll see how we're using it. So that's all what's given. F is given, and then we have a peak hour, which is demand, which is given. So this we've learned in our previous week's lectures, that peak hour demand is always taken as 1.5 times the average demand. So that assumption is again repeated over here. So we need the peak hour demand in order to do this calculation. So let's get, so what are the things that we don't know? So I'm just repeating the formula here. So brake horsepower is equal to water horsepower divided by the efficiency. So we don't know the efficiency, like we know we have two efficiencies. How do we find the efficiency? So we need to find this. So this becomes our first task. We need to find that. Now, in order to find water horsepower, what is the formula? Water horsepower is equal to, the formula goes as it's the discharge, whatever is discharged out of it, and the unit of that is kilogram per second, in discharge in kilogram per second, into the head. Head means the lift. We are talking about the total lift. So it's also called as a total head, which is there. So I forgot. So that's why we are marking it as H also over here. So this is the head due to suction, the head due to discharge, and head due to friction. So they into head divided by 75. So this is a factor. The derivation of how the 75 came is there in the lecture. It's basically because of the units that we're using. So in order to calculate horsepower to this unit, and kilogram per second. So because of that, we're getting this 75. So now in order to find discharge, we need to know. So discharge it's in kilogram per second. So that's given by the density of water, which is W. So that's density of water into the Q, or the volumetric flow which is there, which is in meter cube per second. So because this is in kilogram per second, which means it's in mass. So that's why we are multiplying it with the density in order to convert our volume into mass. So because you know that density is equal to mass. So density is equal to mass by volume. So that is what we are using over here, and we are converting it so into the, yeah, so this gives us the overall discharge. Then we have the head. So in order to find head, we have three factors as we discussed. So first two we know, which acts up to 40, the lift of the pump, which is given 40, plus the friction value we do not know. We need to find this. So this is one factor which we need to find. So that comes over here. So into 40 plus HF we need to find. So now in this, do we know what Q is? the rate of so the supply rate, which is given in terms of LPCD. We have something given in terms of LPCD, so we need to find it for the average population. What is the supply rate, and also the peak demand. So that will be our next task. So we need to find. I'm just marking this as 2. We need to find this Q, because some information is given, but from this information we need to find Q. Now the third task would be to find HF, which is the friction, the head due to friction. So there are 3 unknowns we need to find in order to solve this. So let's go one by one. So the first one, which is the efficiency. So efficiency, so we have 2 efficiencies, the pump efficiency and the motor efficiency. So if we want to find the overall efficiency, since these are operating one above the other, like it's simultaneously operating, we multiply these both, because the effect of the motor efficiency, pump efficiency is multiplied by the effect of the motor that we are using. So the total efficiency would be our pump efficiency multiplied by motor efficiency. So which is equal to, in this particular case, we have the other way. We have 0.85 as the pump efficiency, and we have zero point 0.6 as the motor efficiency. So this multiplied, what do we get? Can someone give me the answer? It's a very simple calculation. I think Galif has not joined today. He's the one who usually gives. Others can also give the
On
answer.
0.51.
Point, yeah, you're correct. 0.51, correct. 0.51. So that's the total efficiency. Now we have the second task, which is to find what is Q. So in order to find Q, which is the average, so first we will, so Q, which is the average demand. So first, average demand we are finding, which is Q, which is we have a population of 1,50,000 into the pumping rate, which is 160. So that comes to around, yeah, can you calculate this and tell me how much this is? Point 0.52, I think, yeah, that's for the previous one. Yeah, 0.51, 0.52. It's okay. So we're taking it as 0.51. And now the overall demand, so this works out to around 24. So I'm just taking all the zeros together. So this will be 24 into 10 raised to 6 liters per day. Is Are you getting this, or is my calculation wrong somewhere? Partha, are you getting this? 24, yeah, 240 into 10 raised to 5, correct. So that's what I've written it as, 24 into 10 raised to 6. Very good, Piyush. So, but this is in liters per day. Now over here, we did mention that our Q should be in meter cube per second. So we need to convert liters per day into sorry, yeah, we need to convert liters per day into meter cube per second. So that would be first into meter cube per day. So 20, so divided by 1,000. So this will be 10 raised to 3 meter cube per day. Now into per second. So that would be, how much does that work out to? So per day into per, you need to convert it into per second.
127 meter cube per second.
Sorry, could you repeat? 0.27 or 127? 0.27, right? Yeah,
0.27.
yeah, point two, yeah, so 0.278 something. So yeah, we can take it as 0.27 itself, meter cube per second. Thank you very much. Yeah, so this is what we're getting as the average demand. Now this is Q. Now we also need to find the, yeah, we also need to find the peak demand. So peak demand is given as 1.5 times this, so 1.5 into 0.278 meter cube per second, which works out to
0.405.
0.405. Okay. Yeah, so we can write it as 0.41.
41.
Yeah, so because I think some value, I took it as 0.78, so maybe because of that I'm getting 0.41. So yeah, so both are around correct. Yeah, 0.41. Correct. So now, so this also we have got. So peak value and Q value both we have got. Now let's find out the third one, which is to find HF. So why we took the peak value is that while we are finding HF, we need the peak value. Whereas when we are using the average, the discharge in this particular equation, we need the average value. So here we use the average value, which is Q, but for finding HF, we use the peak value. So once again, I don't have much space here. I'll just add one more sheet. So now in order to find HF, so the formula goes as HF is equal to F dash into L V square divided by 2GH. So F dash is our Darcy's coefficient, which we discussed before. Sorry. F dash is a Darcy's coefficient, which we discussed as uh, this one point, we wrote it over here, right? Yeah, 4 times F, which is 4 into 0.01. So let's, yeah, so it's 4 into 0.01. So that is our F dash. Now L is this distance, which we wrote over here, the rising main, the distance of the rising main. This is L, which is 300 meters. So let's just start writing that. So we have 4 into 0.01 into L, which is 300 meters. Now V square. So V is the volumetric overall flow which is there, in which we do not know. Like we just know the Q value. We do not know the V value. So we know that this one V is equal to Q by A. This formula we know, or Q is equal to V into A. V is basically the velocity, not volume. So we know the volumetric flow, but we do not know the velocity or the movement in which it's going. So yeah, so if we divide the volumetric flow divided by the area, then we will get the velocity in which it's moving. So to get, so instead of putting as V, I can write it in terms of Q and A, because we know the diameter also. So I'm replacing V with Q by A, which is Q by A the whole square, divided by now our overall formula 2GH. So I'm just leaving it as 2G into D. So this diameter also I'm leaving it as such because we can simplify this further. So A can be written as if you have to so it's pi r square area, because it's a cylindrical pipe, that is what we have. So it can be written as pi r square. Now since d is already there, I'm writing it in terms of d, so it will be pi by 4 d square, right? So if I have to, sorry, yeah, so if I have to write v again, v would be q by pi by 4 d square. So I'm putting that over here. So it becomes 4 into 0.01 into 300 into q square, which is this q square, divided by 2g into pi by 4 d square, which is because of this v square, into, so this one, so it's not v again, it's v square. That's why this q square came, v square. So this whole square into another d, this d. So this again, the overall simplification comes as q square divided by, I'm just writing this simplification, q square divided by pi by 4 d raised to 5, because it's 2 into 2 plus one more d is there outside. So it becomes as d raised to 5. So now let's substitute the values again. 4 into 0.01 into 300 into Q. So Q is what we found over here, which was our peak value, which is 0.41. So 0.41 the whole square divided by 2 into 9.8 g 9.8 into pi m 3.14 we can take it as divided by 4 into now d raised to 5, so d is 0.5, so d raised to 5. So we need to do this calculation. Yeah, so this is a bit lengthy calculation. I'll give you like 2 minutes if we can solve this.
It may be 0.33.
0.33, okay. Anybody else, any different answer? Because I'm getting a different answer.
Hello, ma'am.
Yes,
Ma'am, I have a query.
yeah,
Here it's pi by 4 d square whole square.
yeah,
So it will be pi square and pi
yeah,
square by
yeah.
16.
Yeah, sorry. It will be pi square by 16. Sorry, I wrote it wrong. It will be pi square by
Yes,
16. Yeah. Oh, maybe that's why the answer went wrong. Yeah, it should be pi by 4 the whole square. I wrote it wrong. Yeah. Oh, that's why I'm getting a different answer.
Ma'am, is it 2.66?
No, it's not 2.66. Let's just recalculate once more. Maybe I'm also wrong. Somebody's getting a different answer. Just tell me. I'll just recalculate and check.
Are you 0.35, ma'am?
Yeah, correct. 5 point,
yes, ma'am.
yeah, 5.
5.35.
Yeah, so 5.35, 5.4 approximately. 5.4 is what we are getting over there. So now our total head, our previously we had our head to be 40, which is due to the pump. So our total head would now be 40 plus 5.4, which is 45.4. So we have all the values that we need. So let's just go back and can we fit it here in order to find the, so yeah, so I'm going back over here. Let's find, so now our, do I have space here? Okay, I'll make space here. So our brake horsepower would now be, so yeah, so what's the density of water? So this we I assume that it's known. What's the density of water?
1000 kg.
1000. Correct, yeah. So we are using it in kg only because we said that discharge in kg per second is what we need. So yeah, so that is 1000 into our Q value. So here I said we will be using the average Q value. So that what we found is 0.278. So into 0.278 into head, which is what we found 40, what was it? 45.4. Correct. So 45.4 4. Now this divided by the efficiency. So efficiency, we have already calculated it. Okay, it's 85. Sorry. Yeah, this is point
Point
51. Yeah,
five
point
one.
51, correct. So 0.51 into 75, the 75 factor into 75. So how much does that work out to?
7.32.
7.32. Okay, maybe you can just check once more. I'm getting a different answer.
Um, 329.
Yeah, 329 is correct. 329. So approximately we can say 330 or something. So let's see whether that's there in the option or 329. Yeah, that's a good one. So yeah, so our option C, it's given in a range 300 to 350. So 329 falls over there. So that's the answer. If anybody is getting a different calculation, like you can ask, like if you're getting a different value, you can say.
48.4 is what, madam? I missed that.
No, oh, sorry, this is for my 45.4. Maybe that's why.
That is.
That is the head. That's what we calculated over here. With the
Okay.
friction, we calculated the
Oh, yeah.
head due to pump, and then we added the 5.4, which we calculated. So yeah, so these are all the three values which we calculated. First one was efficiency, which was 0.51. Then the second one was Q, which we took 0.78, and this one was 4.5, right? Sorry, 45.5, 45.4. That's what we have plugged in over here. Right. Any doubts in this question? No doubts. Okay, so let's proceed on to the next question. I understand this was a bit lengthy, so there are multiple small parts which we need to solve separately, and then finally we put it in. So just to give a recap, because there were multiple parts, our intention was to find the brake horsepower, and brake horsepower requires water horsepower and efficiency. Now, to find water horsepower, we need the discharge rate, we need the head and the factor which is there. So, to find the discharge rate, we need to find the volumetric flow which is there. And the question has given us the rate of pumping for per capita in liters per capita per day. So, we need to convert that to meter cube per second for the overall population which is there. That was our one calculation which we did in order to find Q. Then we also, in order to find head, we have three aspects over there: head due to suction, head due to discharge, and head due to friction. Suction and discharge was already given, so we calculated the head due to friction. So that is what we are calculating over here in HF. And then the last one is efficiency. So efficiency, also two efficiencies were given: motor efficiency and pump efficiency were given separately. We have to multiply that in order to get the total efficiency. So that gives us the brake horsepower. Right. So let's go to the next question. From a clear water reservoir 8 meters deep and maximum water level at 50 meters, water is to be pumped to an elevator reservoir at 100 meters at a constant rate of 5 lakh liters per hour. Distance is 1000 meters. Calculate the brake horsepower of the pump. Assume economic diameter of rising main, and F is given as 0.01 and efficiency is given to be 90%. So here the overall efficiency is given. Pump and motor has not been separately given. So just to understand what this question means is that, so you have water, again, you have water at some point, and this is 8 meters, and then you have a reservoir somewhere, and you need to travel it up to a distance of, water is to be pumped at 100 meters. Yeah, sorry, distance is given to be 1000 meters. So this is 1000 meters, and you need to lift it up to, again, 50 meters. So this is what is given to us, the question. So this, sorry, let's come back. Yeah. So this means that our total lift. So we have already discussed what constitutes a total lift. So total lift H is equal to lift due to suction, discharge, and friction. So suction is when you're taking it out. So that is 8 meters, 8 meters plus for pumping up, so that is 50 meters plus the frictional. So that we do not know. We need to find that using the formula which we used before. So this is about the lift. Now again, we've been asked to find the brake horsepower of the pump. So the question is very similar, but what is different here is that the diameter of the pipe was given in the previous question, but in this question, the diameter of the pipe is not given. So they are saying that assume economic diameter of the pipe. So can somebody recollect how we found the economic diameter, or why do we need an economic diameter of it? Yes.
I have one question.
Yes.
You are saying that elevator reservoir is at 100 meter at constant rate. Okay.
Yes.
So
Yes.
it's written at 50 meter, I think. That
No, no, no,
elevated
no. Oh,
reservoir.
sorry. Yeah, no, no. So this total, sorry, I forgot to explain that. Elevator reservoir is at 100 meters. So
Yes.
what is meant is that this overall height is 100 meters. Not this overall height. How do I? Okay. So let's just go to the question once again. So from a clear water reservoir 8 meter deep and maximum water level at 50 meters. So which means that if this water level rises till here, then this would be 50 meters. The maximum water level would be 50 meters. And now from this
Okay.
point, you have to raise it, like the overall is 100 meters. So which means the point to which you need to raise is 100 minus 50, which is 50 meters.
Okay. Yeah,
Right.
sure. Thank you.
Okay. So yes, let's where was so I what I was asking is the diameter is not given. So we need to find the economic diameter. Now how do we find the economic diameter? Can somebody recollect any method which we learned in the lecture? Or what do we mean by an economic diameter? So in the lecture, we learned that when the diameter of the pipe reduces, then the velocity increases. When the diameter increases, the velocity reduces. Also, there are other problems also when you're increasing the diameter, then you have to, like the investment that is required is also high. So considering all these external factors, we always consider an economic diameter, which is suitable for the rate of pumping that we have. So we find this by taking a range of values, that is the economic diameter can lie between A and B. So a range of values, and we use a formula called Layer's method. That's the method that we'll be using over here. So let's get back over here. So let's start finding. So again, to write what is the information which is given. So we have the rate of pumping, which was given to be how much is the rate of pumping? Yeah, it is 5 lakh liters per hour. So 5 lakh liters per hour. So yes, we'll have to convert this. Now, in order to find our friction loss, we also have the distance which is given, which is 1000 meters. Then F is given 0.1, right? F is given to be 0.1. So F is again, to repeat, it's a Manning's coefficient which is given. We need to convert it to Darcy's coefficient in order to fit into our formula. Then efficiency is given to be, sorry, 90%. Yeah, efficiency is given 90%. Efficiency is given to be 90%. So first, let's find the friction loss. So we have H, which is equal to HS plus HD plus HF. So which is equal to, in this case, it is 8 and 50. So it's 8 plus 50 plus now HF. This is what we are interested to find. So let's put it in the formula here. HF is equal to, so the formula which we used before, F dash L V square divided by 2GD, which we derived how we are changing it into 4F, because F is what is given. So 4 times F So converting Manning's coefficient f into Darcy's coefficient f dash, we multiply it by 4. So that's why it's 4f into L, which is this distance, which is given 1000 meters. I'm just keeping it like that. And we are converting V is equal to Q by A. So the same thing. So I'm doing Q square. So we have already discussed the derivation. So I'm just writing it. So into 2G and pi by 4 the whole square into d raised to 5. So this is the formula that we will be using. So now what is important as we're discussing, what is important over here is this D is not given. So we do not know this D. Rest all the information we have. So let's first calculate D. So in order to find D, do I have a page here? Yeah, okay. So layers, we'll use layers formula. So layers formula states that D is equal to 0.97 Q 0.97 root Q to 1.22 root Q, where Q is the discharge. So, so as I said, this is given in a range. So based on the volume of water which is flowing through that pipe, we are calculating the diameter, and it can lie anywhere between 0.97 times root of the flow to 1.22 times the root of the flow. So we do not know Q, we did not find Q. So let's find Q. So we have Q is equal to, it's given, I mean, it's already given. We just need to convert it into meter cube per second. So Q is equal to 5 lakh liters per hour. We need to convert it into meter cube per second. So can we do that small conversion? Liters per hour into meter cube per second.
1.39.
Yes.
1.39 or 0.139?
138 liter per second.
138 liter per second.
138 liter, correct, 138 liter per second. So that will be 0.138 meter cube per second, right?
Yes, ma'am.
Because, yeah, 1000 liters is equal to 1 meter cube. So this would be 0.138 meter cube per second. Correct. So let's plug that in over here. So now our D will now lie between 0.97 root of 138 to 0.122 root of 138. So how much does that work out to?
0.38 meter.
Okay,
0.35 to
0.336, around
0.8.
0.338 is what you're getting. Okay, I got 0.36, so I'm just leaving it as 0.36. It can vary because I've taken it as 139, so 0.1. Yeah, so small variations are okay. So it can be 0.359, 0.36 to 37, somewhere it's correct. And the other one, how much does this work out to? 1.22 root
0.45.
0.5. Point
0.45.
0.45, yeah, that's correct. So here, let's not round it off immediately. Let's keep it as up to 2 decimal places. So 0.45 meters. Now our HF, so HF, because we have two diameters now, in HF we need to plug in diameter. We have two diameters, which means we'll have two HF values. So our HF for 0.36 we will find first, which is uh, using the same formula which we discussed over here. We'll be using, yeah, this formula. So I'm just writing the formula once more so that it's easy. 2G 4 by pi. Okay, this is the formula that we're using. So 4 into 0.01 I'll just erase this off. Yeah, for into 0 1 into, now L is the distance, which is 1000 meters, into, now in this case, yeah, so Q value we have already found, it's 0.138. Now the whole square divided by 2 into 9.8 into 3.14 divided by 4 the whole square into our d value here. So this is for 0.36 that we are calculating. So d value is 0.36 the whole raised to 5. Yeah, so how much does that work out to? Any answers?
Zero point 0.62.
Okay, maybe you can just check once more.
Yeah.
Uh, 14.6.
Sorry, sorry.
14.6. Okay, somewhat near, but still not the answer which I'm getting. I'm also recalculating, so you can just check once more.
Is it 10.15?
Yeah, it is 10 points. Some 10.5 is what I'm getting. 10.15. Just check once more. You're getting 10.15 or I'm getting 10.5. Did I forget to write something?
10.43, ma'am.
10.4 that because yeah, based on the approximations that we have taken, it should lie between 10.4 to 10.6. Yeah, 10.431. Yes, that is the correct answer. So 10.43, I'm taking it as 10.43 meters. So that's our head due to friction. So now our total head would now lie. So yeah, sorry, before we find the total, this was only for 0.36. Now we'll have to find for 0.45. So again, the same calculation will come. So this much will be something which is already there. Only the D value you will have to change. So it'll be the same thing. 2000 into 0.138 the whole square divided by 2 into 9.8 into 3.14 divided by 4 the whole square into here now it will be 0.45 the whole raised to 5. Yeah, so how much does that work out?
Is it 3.42?
Correct. It can be a value between 3.4 to 3.6 based on the assumption. So around 3.45, 3.5, all that is correct. Yeah, so 3.42 is correct. Somebody's getting 3.5, that's also right. 3.6, that's also right. It might be because you might have taken one more decimal point, or you might have rounded this off already. So, okay. So this means that, yeah. So the total head loss would now be, so we already have our head 50 meters for discharge plus 8 meters for suction. So that is our, already we have 58 plus, now in one case we got 3.4. So that 3.4 to, it's a range that we have. 58 plus in the first case, what did we get? 10.4. So 2, 10.43, yeah. 10.43. So our total head loss would lie something between this. So this works out to around 61.4 to, this one would be around 1068.43. So this is the approximate range that we are getting, right? Everybody with me till here? So now let's go back to the question. Our question asked us again to find the brake horsepower. So to find the brake horsepower, we needed to find this head loss. So we have two head loss, so which means brake horsepower will also lie in between a range. So let's find that. So our brake horsepower would now be, again, going back to the formula. So we need the density of water. We need water horsepower. So I'm writing it in one go. We need the density of water into the discharge, which is in Q, into the head, divided the whole divided by 75, which is a factor, into the efficiency. So I'm just keeping this as such because the head is what is keeping on changing in both the cases. To the second, again, this would repeat, and then so this will be our head loss, first head loss range, and then a second head loss range. So this one would be now 1000 into Q is, what did we get Q as? It was 1.138 meter cube per second. So 0.138 divided by 75 into efficiency, it's given as 90%. So 0.9. In the first case, this will be multiplied with 61.4, and this one, the range would be, so this whole term would repeat over here, and that would be multiplied with 68.43. So can we do that calculation?
One 25 to 139.
Yeah, approximately. So if anybody is getting 126, that's also right. And 140, that's also right. But yeah, 125 to 140, anywhere, that's right. So it's 125 to, I'm writing it as 140 to keep a bigger range. So let's see whether that's there in the option. 120, yeah, so this one works. So we are getting it as 125, right? So this one works, 126.5 to 141. Compared to all the other options, this works. So sometimes in your assignment question also, some ranges might be given like this, but because of the assumptions or the rounding off that we are taking, the values might change a bit. So we need to mark the answer which is the closest to the one that we have got. So this is the closest to the one that we have got. So we'll mark 126.5 to 141.2. Right. So any doubts in this particular question? No.
I mean, if averaging is there, then why not to take average of economical diameter 0.36 to 0.45? We want just range. So instead of making lengthy HF calculation for 0.36 and 0.45, we can average economical diameter as 0.36 to 0.45, averaging of that.
Okay. So you're saying and then put it here. So still you will get a value which lies between this both, right?
Yes, 1.5.
Yeah, but the whole reason what you're saying is we need a minimum value and we need a maximum value. So in this particular case where we have been given a range like this, it works. But in practical applications, we don't need. So here you have multiple options. We are just selecting it from the option. But in practical application, when we are actually designing a diameter pipe, or when we are actually calculating the horsepower of the pump that we need to purchase, we have a minimum value and a maximum value. It's not just the average value that we're taking, right? It can be anywhere this value based on the availability of the pump. We can choose. Sometimes there might be pumps like from 125 to 130, one pump will be there. Then 130 to 140, it would be a different grade pump that we're using. So in that case, our average value might get a bit difficult. So we always take the minimum value and we take the maximum value, in and we use that. So here, because you have options, yeah, it makes sense on what you're saying. Calculation, it can be reduced a bit, but this is the correct procedure of doing this.
Okay.
Right. So in most cases, like even in this question, if we are not rounding off any, if we are taking up to 3 decimal places and doing the calculations absolutely correctly, then we will get this value like 126.5, 141.2, like that, this absolute value itself will get. Because here I think 2 places we rounded off, 138, 139 something we rounded off. So that's also one of the reason. And pi also we've taken 3.14 instead of taking 22/7. So based on that, we're getting some small difference. So that's why we are doing this. Fine. So let's go to the next question. Consider the given figure of the mass curve for estimating the storage capacity of the water supply tank. The storage capacity of the tank would be. So we have a figure given. So we have a supply curve, and so in this case, the supply curve is given to be a curved line. So usually in India, normally we have a steady supply, which means it's a straight line. But here it's given the other way, that supply curve is given to be a curved line, and this is our demand curve. So I think it's not mentioned. So this is the demand curve. So we have a difference between supply and demand, and it's given that A is greater than B at this point. That means the excess of supply is less than the deficient of supply. Like for instance, at some point the demand is more than the supply, and that is more. So in this case, how do we find the storage capacity? Do we take the maximum value and then put it as A, or do we take the minimum value and put it as B, or do we take the difference between those, or do we add them up? Any guesses?
Add them up.
Add them up. Correct. Uh, could you explain that also a bit more?
Mm, because we want to have storage capacity for both ones, supply one and demand one.
Yes, very good. Yeah, correct. So basically, we are talking about a time period. So from zero to, so it's a 24-hour pumping period that we're talking about. So if we take only the maximum, which is the supply part, then at some point, probably over here, it's okay. But again, this is the cumulated flow that we are having. So at some point where there's a deficient, it would be okay. But since this is a cumulative demand, the cumulative demand in difference between the supply and demand, A is greater than B. But in an actual terms, in the actual one at a particular point of time, maybe it need not be. So that we will see that later in one problem we will do. So we need to, as rightly said, we need to have the capacity for both. So at some point, we need to store the excess water which is there, which is in this case, we need to store, this is the, no, in B, which is the excess water which will be there, that also needs to be stored. And we also need to store the amount of water which uh, is not pumped at that point. So the demand is higher in this case. So when the demand is higher, for that also we need water. So we also, while use, so this is a mass curve method actually. So in the mass curve method, we always take the sum of both excess supply and excess demand, irrespective of whether the excess in supply is more than the more, or demand is more, or whether initially whatever value is coming, that is more. Irrespective of that, both the maximums we take, we add them up in order to find the storage capacity of the tank. Right. Any doubts in this question? No. So let's proceed on to the next question. So this is a very similar question which we worked before. So we'll just do that once more. From a clear water reservoir 10-meter deep and a maximum water level at 60 meters, water is to be pumped to an elevated reservoir at 100 meters at a constant. Okay, so this is there in your assignment also. So why I took this question is that, so this is the question which is given. It's given at 100 meters at a constant rate of 6,000 liters per hour. There's a small error in the question. It should be 120 meters. This one. The elevated reservoir is at a height of 120 meters. I'll be putting it up in the discussion forum also. So based on that, your calculations might change a bit. So you can make a note of this. So yeah. So in this case, what is asked again is that you have a elevated reservoir. So now this height, the maximum level of this is 60 meters, and the water level which is there currently is at a depth of 10 meters. And now you have another elevated reservoir somewhere over here, and you have your pump here, and you need to pump it. So the total height up to which this is there is 100 meters. So, oh, sorry, it's 120 meters. It was 100 meters in the question, but it should be 120 meters because this height needs to be taken as 60 meters. The height where, so it should be 120 minus 60. 60 meters needs to be taken in order to get the solution. So that's one small error which is there in the question. So you can make a note over there. In the assignment question, it should be 120 meters. Now, yeah, so the question asks us to calculate the brake horsepower and assume the economic diameter. So all this is the same. So let's, do we need to solve this or we can go to the next question? So because this method is clear, right?
Yes, we can go to next question.
Okay, so that this method is clear, we'll go to the next question. So next one is calculate the storage required in MI to supply the demand shown in the table if the inflow of water to the reservoir is maintained at the uniform rate of 24 hours. So this is again, we are using the same mass curve method where we have the supply line, we have the demand line, and we need to find the capacity. So all the storage required. So here so what is given? We just know that the demand in at each for every 4 hours, what is the total demand we know. We do not know. So in a mass curve method, what are the things we need? So we need, okay, for each time we need to know what is the supply rate and what is the cumulative supply. Then we have the demand. Sorry, I went to the next question. Yeah. Then we have the demand and we have the cumulative demand. So here we have the demand which is given, but what is the supply? That we do not know. It just said that there is uniform supply rate for 25 hours, 24 hours. Sorry. So how do we go about this question is we take the average demand, the overall average demand which is there. And if the average demand for 24 hours, if we know that, then each hour, what should be the supply? Or in this case, for every 4 hours, what should be the supply given this is the average demand? So let's first find the average demand. So that would be, we'll just add these up and divide it by 6 because there are 1, 2, 3, 4, 5, 6 time periods. Like for every 4 hours we have taken. So how much does that come out to?
Point 84.
0.84, correct. Yeah, 0.84. So our average demand is 0.84, which means that for every 4 hours, we can supply 0.84 million liters of water. That will be the supply rate, and it's a uniform supply rate. So that's why for every hour we can supply that. So I'm just writing. So this is demand in liters. I'll just add here. It's a cumulative demand in million liters itself. So that would be the sum of all this. So first it's 0.48, then it would be 0.48 plus 0.87. So like that we need to add that up. So let's write that also. So 0.48 plus 0.87, that works out to around 1.35. Then now this 1.35 plus 1.33, so that would be 2.68. Now plus 1, so 3.68 plus 0.82, so that would be 4.5 plus 0.54, that would be 5.04, right? So we have taken the cumulative demand. Now let's take the supply rate. So supply rate, as we got it, the average of the demand, which is 0.84. So for every 4 hours, we are supplying 0.84. So 0.84, 0.84, 0.84, 0.84, 0.84, 0.84. So that's the supply rate for every hour. So now let's find the cumulative supply rate. Just putting it here. Yeah, cumulative supply rate. Yeah, so can we do that calculation? 0.84, 0.84 into 2, it's 1.68. Again, once more, 2.52. Again, once more, 3.36, 4.4, 5.04. Is this what everybody is getting? Right? Everybody with me till here? Can I get some confirmation?
Yes.
Okay. So one thing you can
Yes.
note over here is that because we took the average demand and then we are supplying it for every hour, our cumulative supply and cumulative demand is almost being the same over here, right? So I mean, this can be the case, this need not be the case also in certain cases, but I just wanted to point out that there can be an instance when the cumulative demand and cumulative supply are the same. For instance, if you have a constant supply line and you have the demand which is fluctuating, there can be a point when both are the same, but at that point of time, the supply rate and the demand need not be the same. So here there is an excess in supply. So which means by looking at the mass curve, the cumulative can be the same, but the actual supply rate and actual demand at that particular point of time need not be the same. So this can happen. Again, this the cumulative supply and cumulative demand being the same, it need not be the case for all cases also. Even if you take the average, there can be cases when it is not the same also. So, yes. So now this is what we have. Now we need to find the, sorry, I went to a different slide. Yeah, to come back. Yeah. So, oh, sorry, I'm going to different slides. Yes. So this one, now we need to find the excess. So first, let's see what is the excess in demand, or this is a cumulative supply. So yeah, so let's see what is the first one. Is it excess in demand or excess in supply? So we will be using the cumulative in order to do this calculation, because the storage capacity always requires a cumulative. For that, knowing the information for that particular hour will not do, because we need to store water for a long period of time, right? So it keeps adding up. So we'll take the cumulative demand and cumulative supply, like the difference of this. So in this case, the what is more, supply is more than the demand. So which means we'll have an excess of supply over here. So which is a positive value that we're getting. So we are taking the convention that we are following is that supply minus demand is what we're taking. So 0.84 minus 0.48. So how much does that come up to? Around 0.36.
Yes.
Yes. So that's the first. So this so one way you can do is we can separate two columns. We can write excess in one column and deficient in one column and take everything as a positive value. Another way is that you can take the positive, like in one column itself, we can write the positive values and negative values, and then we can take the maximum of positive and maximum negative. Because previously in the mass curve method, we discussed that we will take the maximum of both the supply and deficient, what is there. So I'm doing the other one. I'm writing positive and negative and going, because I find that to be easy. You can follow whichever method. So the positive, so here this is excess, so that's the positive value. So here also again you have 1.68 minus 1.35, so that's a positive value, and that also works out to 0.36. So like that, can we find the other values also for the next one, which is 2.52 minus 2.68? How much does that work out to?
minus 0.16.
Yeah, so it's negative. So you're taking minus 0.16. So as I said, either we can put excess demand in one column and excess supply in another column and write everything in positive values. That's also a correct approach. So yeah, so sorry. Now next one, 3.36 minus 3.38.
Minus 0.32.
Correct. Next one,
Minus
4.4.
0.0. Minus
Yeah,
0.06.
4.4 and 4.5, right? Minus 0.1. 4.4
Okay.
and
Yes.
4.5.
Yes. Yes.
Yeah. So the last one is the same, so it is 0. So now we need to find the maximum of both. So in this case, the positive values max both are same, so it is 0.36. So we'll have 0.36 plus the negative values, the maximum will be 0.32. So plus 0.32. Now, why some people prefer to put everything as positive values is that eventually you need to add them up. Now, just because this is a negative value, we should not subtract it because it just means that supply is more than demand or demand is more than supply. So it's a sign convention that we are taking. So eventually we need to add them both up. So how much does 0.36 plus 0.32 work out to?
0.68.
0.68 million liters. So that's the answer. So it's there. Yeah, option C, 0.68 million liters. Any doubts in this question? Okay. So if that's the case, we can proceed to the next question. So this is a very similar, it's very similar to the previous question which we worked, but in the previous one, for every 4 hours, there was a constant supply rate and a constant, sorry, every 4 hours, the overall demand was given. So we did all our calculations for every 4 hours, even though it was a 24-hour uniform supply. In this case, for every hour, the supply and demand is given. So, which means the calculations can be a bit, sorry, demand is given. So, similar to how we found the supply, we will take the average for all the values, and then we will take the we'll add the cumulative supply based on the average demand that we are getting. So this is a bit tedious to do manually. So this part we will work it out in Excel. So yeah, I think I'll stop sharing the screen and share the Excel sheet in order to work this out. Manual calculation is also possible, but it takes a lot of time. So how do I stop sharing this? Yes, so right. So is my screen visible now? Oh, yeah, my screen
Yes.
is visible. Okay. So yeah, so let's go to that. So yeah, so that was already worked out. I'll just go. So let's go. So we have the time and demand. So that I'm just copying it from here because I've already worked this out. So this is just to show how we work this out in Excel. So this is what is already given to us. So we have our time for every hour and we have the demand. So I think yeah, here somewhere. No, okay. Cool. So we have our we need, so this is the data. So from the in your assignment also, I'm assuming there is similar question is there. So you will have to take the demand for every hour and write it like this. So it might be given in a horizontal format. So to in Excel you can just transpose it and write it easily. So now the cumulative demand would be, so in this first case the cumulative demand is zero point 0.1 itself. Now in the second one it would be this one plus this, right? So third one again it would be, so I just need to pull this down, so it's the same thing, so which means the previous value which was there plus the next value which is there. So now if I pull it down to the bottom, I'm getting all the cumulative demand. So it's much easier rather than actually calculating it. So let's just check whether we're getting the right values. Yeah. So the previous demand plus the demand in that particular hour. previous demand plus the demand in that particular hour. So we are getting it correctly. So now we have the overall cumulative demand, which means this is our overall demand. So now our average demand would be the overall demand divided by 24, because we are 24-hour uniform supply is what we have. So which is about 0.2479 something. So we can approximately take it as 20.25. That approximation we can do so that it becomes easier. So putting it over here, so previous question what we did. So if we know the average demand for a particular hour, we can say that that is the average supply that we will be giving. So our average supply would be 0.25. So this one, yeah, it should be 0.25 for every hour. So for every hour, 0.25, 0.25. So just if we are double clicking it, then we will get till the values that we have mentioned. We'll get all the values filled. So now the same method. So this one would be 0.25 itself. And this would now be the previous value plus the value for that particular hour. Or we can just keep multiplying it. That's also fine because it's the same value. But this method is right because in case there's a change in pumping also, we just need to change that value. So just doing that. So we are getting the overall pumping which is there. So I'm just checking it again. So at this particular hour from 3 to 4, we have the previous value plus the value in that particular hour. So this is what I said. So in this case, the average, the overall, the cumulative pumping and the cumulative demand is not the same, even though we have taken the average value. So such things can also be there. So it need not be the same always, but even if it's the same, I just pointed out before that the pumping and the demand need not be the same for that particular hour. So now we have the difference. So we need to find the difference between both. So this is where I find the positive and negative approach to be much easier, because blindly we can take the difference of the supply minus the cumulative demand. I'm taking the difference and I'm taking the overall difference for all the columns. So I'm getting the difference. So now I've got both positive values and negative values. So we have to find the excess in supply, which will be the positive value because we have taken supply minus demand. So our excess in supply, let's write excess in supply would be the positive values. So to get the maximum of the positive values from here, I'm taking maximum of this one, the overall table, which will give us the maximum value. So which is 0.55, which is somewhere there over here, right? Then in order to find the excess or the deficient, the let me write excess in demand, because everything in positive I'm just writing. So the excess in demand, that is when the demand is more. So what do we take now in order to find that? Any guesses? Will it be fine if I take the minimum value? My screen's visible, right?
Yes.
Yeah, okay. So now I'm taking the minimum. Yeah, because there was no response. I doubted for a minute whether my screen's visible. So I'm taking the minimum value of all this. So why? Because since it's negative, the maximum negative value is actually the minimum value, right? So I'm taking the minimum, so we'll get minus 0.7, which is happening somewhere over here. So that's when the demand is more, very much more than the supply. So now we need to add them up. So excess demand plus excess supply. So it would be, so now I need to take the absolute value. So in Excel, we have the ABS, which gives us the absolute value, and ABS of the demand also, absolute value, which will give us the total capacity which is needed. So let me just check. Yeah, so that's, yeah. Now, in order to plot the mass curve, so we need to plot with respect to the cumulative. Just go back here, sir. So this is what we need. We need to plot with respect to the hours. We need the cumulative supply and the demand. So I'm just copying these values here because Excel, it's easier if we paste them separately. So I'm taking the cumulative demand now. Cumulative demand, sorry. Yeah, so since that's already calculated, just pasting the values. Cumulative supply, just pasting the value so that the calculation doesn't get disturbed. Yeah, so now this I can plot. Oh, sorry. Okay, I think we'll have to plot them separately. I don't remember how. Yeah, so cumulative. Nee, what just happened? Yes, it's coming in this. Ha. So we just need to take the line chart for with both the values selected. Okay. So yeah, so this will give us the difference in cumulative supply and demand. So as we said, the straight line which is there, that is a cumulative pumping or cumulative supply that we have. And the demand is fluctuating, so that's what we have. And towards the end, it's more or less the same because you've taken the average value. It won't be very different towards the end, but it need not be the exact same value also. So our maximum demand is happening somewhere in our fourth to fifth hour, which is over here. So this is where our maximum, excess in pumping is there. That means supply is more than the demand. You see the blue line is below. Then our maximum demand is happening somewhere in the 18th or to 19th hour, which means 6 p.m. to 7 p.m. So at that time, we have around excess in demand. So if you observe over here, we are getting these two peaks and finally we are adding these two peaks up in order to get the overall capacity in million liters. Is this clear?
Yes.
Okay. Thank you for that confirmation. So now I'll go back to the previous one. Yeah, I'm just sharing my presentation again. Right. So yeah, so this is where we were. Is my screen visible? No, it's stuck. One sec. Yeah. So this is the question. So the answer that we got was around 1.5 million liters. Sorry, 1.25 million liters is what we got from this calculation. So this was the Excel sheet which I was showing. So now here it's given in I think it's given in liters. So 1.25, so it becomes 1 million liters it was. So this would be the answer if you're converting it into liters. Yeah, so the question was the required in liters. So that's why this conversion is done. Right. So we're proceeding on to the next question. In the figure given below or in the side, x2, x4, what does x2 and x4 represent? So we have the demand line, which is the straight line. So again, in the previous one which we worked, the demand line was fluctuating and the supply was changing. But here the demand is a straight line and the supply is fluctuating. So we have supply. So this is supply which is there. So what does this x2 to x4, which means it's this much. That means from this point to this point. What does that show? Is it the accumulated supply, storage required, accumulated demand for the period 1 to 2? So this is 1 to 2. Is it the accumulated demand or is it the surplus in the reservoir? Can any guesses?
Surplus in the reservoir.
Uh, so we have been asked 2 to 4. So the surplus in the reservoir wouldn't the surplus in the reservoir be this whole value? Because this is a demand and this is the supply. So for we have that much of so and this is cumulative. So at that any particular so if the surplus in reservoir at point 1 would be this much. That's why we designed the reservoir also. So it's not this small value. It will be this, or if you're taking it as 0.2, it will be this entire value, not the small value. So it's not the surplus in the reservoir. Anybody else? Any other answer? Is it the accumulated demand for period 1 to 2?
I think no, ma'am.
Yes. Why do you feel it's not?
Ma'am, it falls under second one. So thing doesn't come between 1 and 2.
Correct, yeah. So the accumulated demand would something be somewhere between here, like it should be something here. It wouldn't be this x2 to x4. It has nothing to do with demand, in fact. It's a separate supply curve. It only talks about the supply curve. It's not even touching the demand curve. Sorry. So it's not the accumulated demand. And is it the storage required? Anybody, is it the storage required?
I think no.
No, because yes, so that's what we've been discussing. Storage required again needs the oh sorry yeah, storage required again needs the maximum between supply, and so we'll need this value, which is the surplus in the reservoir in this case, because in this case again there is no point where the supply curve is going below the demand curve, which means it'll always be a case where there is surplus in the reservoir. There'll not be a case where not just reservoir, there will not be a case where there is water is deficient. So it will not be storage also. Why? Because storage will take this whole value. So for this particular point, it is the slope. So the idea is that if we have, so the demand curve which is given is a redundant curve. We don't need that. The slope in the of the reservoir, the slope of a mass curve, if this is a supply curve, the slope of the if you take 2 points and if you take the slope of that, which means the difference in heights between these 2 points, will actually be the accumulated supply that we are having. Similarly, if we were asked this line over here, what is this? Then that will be the accumulated demand which is needed for that particular point of time. So the slope of that line, or the height which we need for from one point to this point, will be the accumulated supply or demand. So in this particular case, it is the accumulated supply. Is that clear? I'm sorry, I'm having a bad cold. Yeah. Is it clear?
Yes, ma'am.
Okay, we'll proceed on to the next question. So this is also a calculation. So the estimated hourly consumption of water for a town at the ninth hour is 6.1 million liters per hour. So per hour it's given. So for one particular hour it's given. So it's said that for the ninth hour is 6.1 million liters per hour. The pump can supply water at a uniform rate of 1.5 meter cube per second. Now, the water required to be augmented from a storage reservoir in million liters per hour is. So, we have the supply which is there in that particular hour. So, as we discussed, at one particular hour, the supply which is coming may not be adequate enough uh, in order to supply for the demand which is there at that particular hour. So that's the whole point why we have a service reservoir also. It balances the demand. It stores excess water and it gives out. So if this is the supply rate and if this is the demand, what should be the excess that we are taking from the reservoir? So it's a very simple question. But the catch over here is these two are given in two different units. So our first task would be to convert them into the same unit. So let's write what is the demand. So the demand is given to be estimated hourly consumption is given to be 6.1. So 6.1 million liters per hour is the demand. So now let's look at what is the options, like the storage which should be augmented in liters, million liters per hour. So which means this is the unit that we want. We should not convert this. So this is okay. Now what is the supply? So our supply is coming to be around 1.5 meter cube per second. So now we need to convert this into million liters per hour. Can we do that conversion? So meter cube into liters, so into 1000, second into hours, so again into 3600.
5.4.
Correct. So that will be 5.4 million liters. So yeah, unit I've already written. 5.4 million liters per hour. So now how much should be augmented from the reservoir? So it's basically the demand minus supply, right? So we have the demand of 6.1 minus the whatever supply that we are getting is only 5.4. So this difference will be the value that needs to be augmented. That is
0.7.
correct. Yeah, 0.7 million liters per hour, which is there in our option D. So this is a very simple question, but the only catch is this, that if you don't convert the units, then we can go wrong. Okay, so I think this was there in one of the GATE papers before. It's not there in the previous assignment, but in one of the GATE papers it was there, so that's why we included this. So yes, so question 9, the different applications for pumps are A, for lifting water from the high quantity, low pressure from a high quantity region or a low pressure region from a well or a treatment plant, for pumping water into the distribution system to boost the pressure within the distribution system.
All of these.
All of these, yeah. So this is there in our first pumps, the chapter itself. We are discussing that we're using this for lifting water, for pumping to distribution systems. If we're using it for both, then there'll be two pumps. Then we also use it to boost pressure. So these are known as booster pumps. If you're using it to boost the pressure, it's known as booster pumps. And if you're using it to lift, what are they called? You remember? We have high lift pumps. So these are the two pumps that we learned. So high lift pumps is used in order to lift water, and we use booster pumps in order to boost the pressure in the distribution system. So the answer for this is all of this. Oh, I think I just answered this question. I'm sorry. So yeah, that dash pump directly pumps into the distribution system, whereas dash increases the pressure and are located anywhere in the pipeline. Yeah, so I just answered this. So what's the answer for this?
Option A.
Option A, correct. Yeah. So we have the high lift pump, which pumps directly to the distribution system, and then we have the booster pumps, which increases the pressure and can be located anywhere in the pipeline. Correct. So that's it. Now, next one. In the mass curve method, the storage required is taken as the sum of dash ordinates between demand and supply. Is it the maximum, minimum, or average?
The maximum.
Maximum. So this also we have already discussed. Because we already solved the question with the mass curve method, we already saw that we take the maximum value. We don't take the minimum value. So if this is demand, this is supply, and this is demand, we always take the maximum. So the answer is maximum in this case. Good. Let's go to the next question. A service reservoir design depends upon which of the following? Reservoir capacity, topography of the site, cost of materials such as concrete, reinforcement, and formwork, all of this. Any guesses? I mean, it need not guess. I'm sure you all know the answer. Yes, Piyush.
All of
this.
these.
Yes. Manoj, you want to say something?
And yes, all of these. All of these.
These. Correct, sir. Yes. So it's all of this because the reservoir capacity, that's what we discussed in the previous questions also. How do we design the reservoir capacity? Now, topography of the site is also important because if it's a very undulated surface or a slopey surface, then we will have to design a reservoir or plan the structure based on that. Then cost of materials is also important, what we're using. So we've discussed in our lecture, like in the early days, we used to have a rectangle reservoir, which was not an efficient method. Now we designed the reservoir in a much more, what do you say, capable, like for the storage or the design, the overall design considers the overall storage capacity, and the form is also designed in such a way that minimum amount of support or the center of gravity of that water is balanced by the support that we are giving. So with time, we have improved the reservoir design also. So now if it's in a very if the topography of the site is different, then based on that, we'll have to modify our design again. And yeah, cost of the material. So yeah, so this is a very straightforward question. All of them are important. Now the total storage capacity of a storage reservoir is the sum of balancing storage plus breakdown storage, balancing storage plus fire storage, breakdown storage plus fire storage, balancing storage, breakdown storage plus fire storage.
D.
B.
D.
D.
All the three.
All the three: balancing storage, breakdown storage, and fire storage. So, what is balancing storage firstly? Yeah, so what is balancing storage?
Storage required for demand purpose.
For demand purpose, okay. Or basically, it's the whatever mass curve method which we discussed before, the balancing which is there. For instance, if the demand is excess or if the supply is excess, in order to balance this out, balance the difference between the cumulative demand and cumulative supply, we use the balancing storage. So in all our calculations, we mainly calculated the balancing storage. Now, in addition to those, we also need to accommodate for the breakdown storage and fire storage. Now, what is breakdown storage?
For maintenance purpose, if we are
Yeah, so maintenance purpose, or at some point if the pumping is stopped, or if the this one the supply is stopped, or there's a breakdown on the overall system, we need some amount of water which is already. So it can be for maintenance, it can be because of some pipe was broken or some factor, like whatever factor. So if there is some breakdown on the overall system, we need some storage in order to keep the system running. So we take about 25% of the average daily consumption is usually taken for this breakdown storage. Now, then we have fire storage. This we have in the previous initial lectures we have discussed about how much should be the fire supply when there is a fire. So based on those factors, we also reserve some water in the reservoir for fighting fire in case there's a fire outbreak. In order to fight that, we store something also. So this is what we learned in our lecture. So we have the balancing storage, which is the for equalizing the balance against the variable demand against this constant supply. So this is the balancing storage. Now the breakdown storage, as we discussed, it takes about 25% of the total capacity. So sorry, before I mentioned 25% of average consumption. No, it's 25% of the total capacity for which the reservoir is designed for. And then we also have, or the other option is we take about 1 to 2 hours of the daily average supply. So 1 to 2 hours, what is the quantity which is required, that we reserve, or we take 25% of the total capacity. Then we have fire storage, which usually we take about 5 liters per capita. So based on the population, even while calculating fire demand, we also saw that population or the volumetric flow is calculated based on the population. So that's important. So usually we take about 5 liters per number of people who is there. Right. So let's go to the next question. The economic depth for any service reservoir depends upon breakdown storage, total storage, and balancing storage. None of these. What do we mean by economic depth? Economic depth basically depends upon, if we have a reservoir, what is the capacity or the depth to which we are designing it for. So, does that depend upon the breakdown storage, total storage, balancing storage, or none of this?
total storage.
Total
Total,
storage.
correct, total storage, because total storage will account for our balancing storage and breakdown storage plus a fire storage. That's what we discussed. So, it needs to be designed for the total storage. Right. So now this is our last question. Dash reservoirs are most economical and used in case of large capacity, whereas dash reservoirs are preferred for small capacity. A circular is preferred for large capacity and rectangle is preferred for small capacity. B, elliptical and hexagonal, circular and elliptical, and D, rectangular and elliptical.
Circular and elliptical.
Circular is preferred for in case of large capacity, correct. Now dash is reserved for small capacity. Elliptical is preferred for small capacity. Okay. Anybody, any difference of opinion?
Circular and rectangle.
Circular and rectangle, yes. So why rectangle is preferred with small capacity is because it's easier to build a rectangular one. When you look at the cost, when you look at the design calculations, everything, rectangular is easier. And with small capacity, that is enough. A rectangular reservoir will solve the purpose. Elliptical, again, it's not very easy to design because you need to consider a lot of factors. The forces need to be ensured to one single point. So it's not very easy, and mostly we don't we always prefer circular and or rectangle. So the answer here is circular and rectangular. So we have a circular reservoir for, sorry, large capacity and a rectangular reservoir for small capacity. So yes, so that's all with the questions for that I wish to discuss. Now, if you have any doubts in any content from week 1 to week 4, you can ask. Have you all registered for the exam?
Yes, ma'am.
Okay, good, because I think
No, I'm not.
not yet. Huh? So then register soon, because the deadline's extended now, and they might stop the registration soon. So it's better to register soon. And exams will
Okay.
be more or less similar. Like I saw in the discussion forum, somebody had asked what would be the pattern of question paper. So it'll be very similar to what we're doing in the assignments, whatever we're discussing. So I think most of the questions which are apart from the assignment also, which are usually dealt in GATE or other competitive exams, that also we're discussing in these live sessions. So it would be mainly along those lines itself. So it shouldn't be easy. The calculations and all would be very similar to what we are doing in the live session. So it'll be easy. Right. So just one point to keep in mind while solving this week's assignment is that one question where the discharge lift should be taken as 60. It should be taken as 60 itself while doing the calculation. I hope you have made a note of that. Right. So if that's the case, we can call it a day. Can we?
Yes, yes, ma'am.
Okay.
You are already going through fever or something. So let's close.
No, I'm fine. I'll be there till 9. Yeah, I mean, I'm having a slight fever. The weather is a bit odd, so I hope next week I'll be like completely fine. So yeah, I'll be there till 9 o'clock. So if you have any doubts, you can always ask. If there's no doubt, we can end. You can leave the session. Thank you all for joining, and thank you for being very enthusiastic today. Like I guess most of you were, it's not enthusiastic, interactive today. That helped me also in today's session. So that's good. Looking forward to similar sessions in the coming weeks.
Sure, ma'am.
Thank you, ma'am.
Yeah, thank you.
Thank you.
Yeah, so I'll be there till 9. You can all, if you have no doubts, you can slowly leave.
Thank you, ma'am.
Yeah, thank you.